Hi, so the next thing that we're going to be talking about today is starting to dive into Rosetta. We've talked about like C++ and Git and how you might work with Rosetta. So this will be your first introduction to some of the components in Rosetta and how they all come together. So just a quick overview. You'll be doing a lab today where you'll try to build your first Rosetta protocol. You'll load in a structure of a protein, you'll try to move it, score it, and take a look at it through an interactive viewer in PyMol. And what this will do is it'll give you some exposure to some of the basic objects, tasks, and tools in Rosetta. So those objects would be pose, ScoreFunction, and a move map. Tasks like using the Monte Carlo object, packing and minimization. And then some tools that will help you to develop this protocol, which is the development factory, options, and random number generators. So just kind of taking a step back and looking at the big view, Rosetta does a lot of things. We started today, it's about 1.7 million lines of code. And it does things from folding to loop modeling to docking and to protein design. But what's really cool about the object-oriented design of Rosetta is it allows us to reuse a lot of these different building blocks that you might use towards sort of building a protocol. So I'm not sure if many of you guys are familiar, but Rosetta uses this sort of Monte Carlo approach. So what you'll do is you'll load in a protein structure or starting structure, move that protein structure. So you can see, like in this case, this helix sort of moved from on the x-axis to along the y-axis. You'll score a structure, and then you'll use the energy of that structure to evaluate if you should accept it or if you should reject it. And going forward, you'll use that to determine which structure you can use in the next iteration. And Rosetta does this a lot of times. You'll go over and over, and you'll keep moving and scoring and moving and scoring iteratively until you move toward your final structure. Now, that's sort of an abstraction of the big picture of what some of the different Rosetta modeling protocols do, but hopefully it'll help you sort of walk through what some of the basic building blocks are that I'm going to talk about as I walk through this with you. So the first sort of essential task in Rosetta is to load in your starting structure. How does Rosetta represent a pose? How does Rosetta represent a protein? What's in it? And what code structure is used for that? So Rosetta represents a protein structure using a data structure called the pose. The pose represents the molecular conformation that you're working with. So this can be nucleic acids, ligands, anything that you can stick in a PDB, you can read into a pose and work with. So this kind of shows you can really sort of stick a lot of different types of molecules. And the pose, so the pose is an object in Rosetta, and there are two main things that are sort of inside the pose. The first is an energies object. So when you score a pose, the energies object stores the different energies as a result of that scoring process. So there are different types of energies that I believe we'll talk about later in the week. Long-range interactions, short-range interactions, scoring per residue structures. I can't see it, so. Next is confirmation object. Confirmation is what will store all of your XYZ coordinates, residues, and you'll go along and list your degrees of freedom in that confirmation object. These do a lot of other things. We'll talk about them later in the week, but this is just sort of the basics of the pose and what's kind of inside it. So if you want to use a pose in Rosetta, you'll use the core import pose package. So when I say, Andrew talked about namespaces a little bit earlier today. A namespace is what allows us to sort of group different files in Rosetta together and associate them. So when I say using namespace, it means I'm using a method from that particular namespace. So to load in a pose, I'll create a new pose object. So the pose ending pointer would be in the core pose package or namespace. And then the pose from PDB method is probably the most common call you'll make to take a PDB file that you have, so my PDB file.pdb, and load that into your pose object. And this method will basically read through that PDB file, load in all of your residue types, coordinates, and so forth, so you'll have an initialized pose object. So now that you've loaded in your starting structure, the next task that you might want to do in Rosetta is to move it. But before you can do that, Rosetta has this data structure called a move map. And the purpose of a move map is to tell you what you would want or allowed to move. So specifically, you can call, you'll create an object, it's in the core kinematics namespace, and you'll just create a move map object. And there are two particular settings that we're going to talk about. First, you can set backbone torsions to movable. So when you're iterating along a pose, you can allow phi and psi to move. And then you can also set chi torsions or sidechain torsions to movable. So if you set chi true in your move map, if you minimize or you pack, those different angles will be allowed to move as well. You don't necessarily need a move map to do this, but the first sort of step to moving things in a pose, we'll talk about later in the week. We have things called movers, which will allow us to make some larger scale moves or different types of moves in the structure. But the first type of backbone move we'll just talk about is sort of explicitly setting phi and psi angles or picking random phi and psi angles to change. So the way you can do that is just through directly interfacing through the pose. The pose has two methods, pose.setPhi, and you can set the residue that you want to set phi to, and then your new phi value, and you can do the same with psi value. And this is sort of the first step of how you can start working through the pose and making changes to the backbone angles. And this is sort of if you can sort of like imagine in a protocol, if you have, this is just like a 3 residue peptide, you can sort of walk along the structure and start moving some of those torsions. This is sort of more, how realistic this is like versus teaching, but it's good to sort of know how you can start making changes to the structure of the pose by interacting with the class directly. So after you've moved your structure, the next thing you might want to do is to actually score it. And the class that you'll use for this is the ScoreFunction. The ScoreFunction and all scoring related things most likely live in the namespace course scoring. And a ScoreFunction is just a linear combination of different energy terms. So you might have heard of like the attractive or repulsive terms in Rosetta. I think right now there's something like 150 different terms between different energy functions, and they do all different types of things. There's terms for membranes, RNA, DNA, and regular protein structures. And you just, if you're evaluating the total energy of a structure in Rosetta, you're basically summing the weights of each term. So how this actually happens is Rosetta, the ScoreFunction internally stores a vector of score terms and a vector of weights, and then you just compute the dot product between those, and you can see you get your linear combination of terms. And what's kind of interesting about this is what really happens is in that ScoreFunction, it's initializing all of the energy terms, but it's only evaluating the non-zero weighted ones. So in this sort of toy ScoreFunction, there's only 5 terms, but in Rosetta, there's, I think, almost 200. So you only want to evaluate the terms that are relevant. And that can be done by specifying this in a weights file, which I'll talk about in a second. So to interact with the ScoreFunction in code, there are a couple of ways that you can do this. I know some are preferred over others. The first is you can just sort of create your own ScoreFunction by manually setting the weights of score terms. So you can create a new ScoreFunction object, and then just sort of manually set the weight of my term, and weight is just a real number. I think you can create the Teleris energy function by using this method getScoreFunction. That belongs in the ScoreFunction factory. And then finally, you can create a custom energy function from a weights file. You can find all different weights files in the Rosetta database by calling createScoreFunction and then specifying I think got cut off, but the weights file that you'd want to create your scores from. So like an example, like something like a weights file would look like is so it's just going to sort of like list the terms. And then the createScoreFunction method will just go through this file and say like associate these terms with these weights just like you would if you were to set it manually. So other things to know about the score function, so to actually score a pose, which is probably the most relevant operation, you can just call ScoreFunction or the score method, and it just takes a pose, and it will store the energies in the energies object. To access those energies, there are a lot of ways to do it. One way is to just call pose.energies. You can usually access individual energy terms, and you can also print out using pose.energies.show. Is another way if you're just running an application, you want to see the resulting scores in sort of the intermediate instead of like printing out to a score file. And so now that you sort of have some of these basic building blocks to score a pose, the next and sort of more relevant task is how do you kind of put it all together? So that's done, you'll use it later in the lab, you'll use a Monte Carlo object. And what this object does is it stores two poses. The original pose that you had, the one that you last made the move from, and then the new pose, so the one that you applied the move to. And what it will do is it will compare the total energy of the last pose, or the last accepted pose, and the energy of the new pose. And then what this object will do, if you call mc.boltzmann, it will evaluate which structure you should accept in your simulation. So if the total energy of your new pose is less than total energy of your old pose, you'll accept the new pose. If not, you'll use the Metropolis criterion to accept. So you pick a random number from 0 to 1, and then you say if that is less than, if the accepted probability is less than that number, then you'll accept the new structure. So those are sort of some of the basic components of doing a Rosetta simulation, but it's a lot more than just like making small backbone moves or small different moves. There's a lot of like optimization and packing. So to pack sidechains in Rosetta, you'll use something called the packer, which I'll talk about in a minute. Packing involves making different Rotamer substitutions, where Rotamers are these discrete sidechain conformations that come from the Dunbrack library. And basically what you can do is you pick out of this library based on a given phi-sci what some combinations of possible Rotamers will be, and you'll make these substitutions in the backbone. So you can see this is an example of just different Rotamers of one amino acid side chain being substituted. That's kind of an idea of what happens. And what actually happens when you're packing is you iterate from high temperature to low temperature. And you're randomly performing these Rotamer substitutions and evaluating the energy at each step. And in a similar manner you'll accept more favorable Rotamers and then accept the conformation that had the best energy from that packing cycle. And yeah, so you can sort of see some similarities to this whole process where you're saying, I'm making a change in the structure, I'm scoring it, I'm evaluating the move, and then I'm deciding if I want to accept. So to use the packer lives in the core pack namespace. There are two classes that are relevant, and Andrew will talk about more later in the week. The first is a packer task. This controls packing degrees of freedom, options, Rotamers, and temperatures. And the task factory is the class that will generate a packer task. I think these are the two that you'll interact most with. And to set up for packing, so there are two sort of namespace groups that you're using, core pack and core pack task. You'll create a new packer task. You do that through the task factory. In this case, in this lab, we'll do something called restrict to repacking, which means that you're just going to sort of make individual Rotamer substitutions instead of in a case like design where you'll make, I think, whole amino acid substitutions, or there's different options there. And then finally, you'll make calls to pack Rotamers, where pack Rotamers takes a pose, a score function, and a repack task. And that's where you'll start to interface with the packing task. And then sort of next, we'll talk about minimization. So minimization is when you iterate through the degrees of freedom in a pose, which is bond length, bond angle, and torsion angle. And you'll update these and also sort of evaluate best energy. And the way to interface with the minimizer is through the package or the namespace optimization. So the way to set up is you'll set up minimizer options object. There are lots of different option combinations you can use with the minimizer. And then you'll run the atom tree minimizer on your pose. So you'll take a pose, MM is move map, a score function and minimizer options, and you'll be able to go through that minimization process as well. Cool. So I talked about some of these core building blocks that are part of Rosetta. But there's a lot more than just sort of these pose and score function objects. What's also important is knowing how to tie them together in an application so you can actually start building your own protocol. So these are just sort of a couple topics that will help you to do that. The first is namespacing, which we've already sort of covered a little bit. A namespace is a container that will help you to organize different objects, files, and classes in Rosetta. Why would you do this? It's really helpful for organizing large projects. So think about if all of the classes in Rosetta, things like ScoreFunction, pose, they all lived in the same place. It would be much harder to differentiate which objects are related to which tasks and so forth. It makes working in Rosetta a lot easier. And in Rosetta, what we do, it's a coding convention to organize your namespaces, like the directory structure. So if you have the file core score function, that would go in the namespace core scoring. And it becomes this more reliable way to access a class. And so namespacing has some benefits. You can have two classes that live in different namespaces, and you won't get collisions or confusion. So a lot of namespaces in Rosetta have a util class that tends to show up a lot. And then another effect is that a set of related classes can be grouped by name. So things like ScoreFunction factory will all be grouped together. Another thing to know about is naming conventions. When we create new class files in Rosetta, we always name them camel case, so uppercase letters for each of the words. And then we talked about earlier, when you set up a class, it's always really important that you set up a forward header, which is declared in the header file, and then that class will get implemented in the CC file. That's a pattern that you'll find a lot, or should always find when you're working with classes in Rosetta. And these are just a little bit of the coding conventions, but we'll be talking about them throughout the week. And then some sort of more tools and things to be aware of. You guys should have already had experience working with Scons and building, but these are just sort of the commands to remember. Scons is really useful because it will only recompile the code that you changed after you've sort of done that large initial compile. To build the code, you can just use scons.py. To build one app, you use scons.py, and then you can specify that name of the application that you want to build. For building executables, you can specify bin, mode, release, or debug. And then to build the unit tests, specify scons.py and then cat test is the keyword. Next, so Rosetta has its sort of own set of types that we use instead of some of the standard types. So in core, there's a file called types.hh, and you should see these different types sort of scattered throughout Rosetta. It's good to know what they are. So a core size is just type def from a platform size. This is just an unsigned integer. So you shouldn't use ints. I think you're supposed to use core sizes. A core real is type def from a platform real. This is in other languages double. And then a core vector is a numeric an XYZ vector, so just XYZ 3D vector. These will show up a lot throughout Rosetta, and they're useful to know about. Like some of these have additional functions that are useful to call, like XYZ vector you can fill. And then also some more useful types. It's good to know about utility vector ones. We just talked about these are sort of typed up from standard vectors. And you can resize and work with these vectors. And so the way you'd set one up is if you have a utility vector one, you could specify my type could be like a real, a core size. To set an element, you can just directly set the element if it's already sized. Or you can just, if you can initialize an element and just push back, it means to just add an element to the array so you don't have to size it beforehand. Another good thing to know about is the option system. So Rosetta has a really large sort of set of options that we use to interface on the command line with different executables. So if you've ever run relax, or like if you've just loaded in PDB, you might have used the in-file-s option. That's the option that people use to specify PDB files when they're running Rosetta. What's good to know about is how to add an option to the option system. You'll do this through an options rosetta.py script. This is a script that's set up with where everyone sort of adds their options to the option system. And this is sort of what the syntax looks like inside that file. There are option groups. That's how options get sort of grouped into these namespaces. So you have a group in, a group file, and then for the option S, or the PDB file, you have a description and then a type. So in this case, it's a file vector, or you can get a string of files by working with this option. And then once you've added a new option to that options rosetta.py script, you can actually run the script option.py to add your option to the system. Or I think now Scons will actually add it for you. We have that script running every time you compile. So you're adding the option to options rosetta.py. I think if you wanted to add it by yourself, you can run options.py.
So the options rosetta.py is loaded as a module when options.py runs. And option.py is now run by default when you use Scons. So you won't have to do it manually.
Yeah. So yeah, you definitely don't have to run that anymore. It's something you used to have to do, but I guess it's good to know about. And then, so now that you've added the option to the option system, the next question would be, how could I get access to this option in code? I want to set something from the command line. So the first thing you do is you would pound include the header file that option is described in. So they're described in these option keys files. Using namespace basic options is just convenience. You could also write out the entire namespace. And to access the option, you can use the options object, and then specify in-file-s, and you can just read in the option directly from there. And then to specify it on the command line, which is what you might be more familiar with, you just use -in-file-s and specify your PDB file name. Another cool thing to know about is random number generators. There's a lot of utilities in Rosetta for working with random numbers. These will also be discussed a little bit later, but what's useful to know about for now is if you just want to get a random number from a Gaussian distribution, you can just call numeric random Gaussian, and we'll give you a number and 0 to 1. And then finally, the last thing I'm going to talk about is writing a pilot app. So pilot apps are the forum that Rosetta uses to start developing protocols. These are executables like you worked with the homework, where you can just write code directly in the file, compile it, and run it. Pilot apps are often where applications that are in development will eventually mature to public apps that you might be more familiar with, like Relax or Ab Initio or docking. And they tend to have a uniform format. You'll see int main, and then specify your your arg arrays. And then there's some important characteristics of it. Is this devel init. That's what initializes things like the Rosetta option system and JD2 and things that you might need. And then we'll also usually surround this with a try-catch block that'll throw an exception if that were to fail. That's usually good to make sure your program terminates nicely if something were to go wrong, versus just sort of like terminating nasty and you don't know what's going wrong with your code. Yeah, and then I guess finally, the thing that you'll be working with today is a cool utility in Rosetta called the PyMol Observer. You might have worked with it in PyRosetta before, but what you can do is you can add an observer to your pose so that when your pose updates, it will send the structure to PyMol, and you can actually view it as you're doing the simulation. So the way you'll do this in the lab is you'll use add PyMol Observer to add the PyMol Observer to your pose. And then in your PyMol session, you'll run the source Python bindings PyMol PyRosetta server. And then when you run your pilot app, as you update the structure should show up in the PyMol Viewer. And you can read more about this. There's documentation for this on the wiki. Cool, so now we're going to do a lab. This will be sort of your first lab interacting directly with Rosetta. You'll load in a pose, score a pose, try to make random 5-side perturbations, repack, minimize, and then interact with the Monte Carlo object. And yeah, that's it. So are there any questions? No? Okay.
Yeah, I have a question. So I noticed that there's 4 core files, like core 1 plus 2, 3, 4. But I dipped them and it seemed like I had all. Like, do I do something wrong or something different?
So you might be looking at, so I know there's like a core.1 and then a core.1.source.settings file. So
I think it was like the settings were different, but the cores were the same.
yeah, so the settings files are the ones that you use to actually add the files to the build system. I don't know why those extra files are there.
So Scons won't try to build a particular library unless it has the name of the thing that is in the directory. And so it used to be that there was just one core library and there's one core.source.settings file. But when we split core into 4 separate libraries, then Scons no longer saw that there was like, you didn't see a core.1, so it wouldn't try to build, or it wouldn't look at core.1 and source.settings file. So we just added extra empty files, and Scons sees that they're there, doesn't look at them and really do anything with them, and then it builds. So there are also like tons of these like protocols in the school f.7, but these things are not. And they're also the same. They're just empty files.